Hi, everybody, and thanks for coming. My name is Ray, and I'm a PhD student of the Computer Vision Group of TU Munich. Today, I'm going to introduce you our recent work on online photometric calibration, which is a joint work with my student, Paul Bergmann, and my PhD supervisor, Daniel Cremers. So the basic idea is we propose a pipeline to recover the camera response function, the vignetting, and the exposure times in an online fashion, enabling plug-and-play photometric calibration. So, as you know, Odometry and SLAM have seen tremendous successes in robotics and other domains. The most prominent examples are, for example, here, PTAM, SVO, or SLAM, or DTAM, LCD SLAM, and DSO. So generally speaking, there are two families of Odometry or SLAM. The first three belongs to the family of feature-based method, and the second three belong to the family of direct method. Recent progress of direct method has shown superior performances over feature-based ones on certain datasets. So here is an example of the performance of DSO and also of SLAM. The fundamental assumption made by direct method is this so-called brightness constancy assumption, which is actually also the basic assumption for many other applications, such as stereo matching or dense optical flow or thin flow estimation. To make this assumption hold, people usually need to perform the photometric calibration. If you don't do this in practice, then the brightness constancy assumption will be violated, so which will lead to the performance of direct method will drastically decline, as shown here with the black curve here. So what is photometric calibration? To understand it, we need to go through the image formation process. Imagine you take a camera and you take a picture of some scene, and you first need a light source. Then some surface will reflect the light. And the amount of the reflected light is called radiance. And this radiance will go through the camera lens, where it will suffer the vignetting effect. And the radiance will hit the camera sensor and will be accumulated there during the exposure time. And then the accumulated radiance will be considered as input to the camera response function. And as output, you get the pixel intensity. The entire approach can be summarized into this equation shown at the bottom. So from right to left, we have the radiance, which is denoted by L here. And we have vignetting vector V and exposure time E. And these three parts are input to the camera response function F. And as output, we get the pixel intensity O. On the right side, I give you a real example of these three factors. So the first one is the response function, and the second one is vignetting. And at the bottom, you see the exposure time of one sequence captured by using one camera. So you can see it changes a lot. So given a distorted sequence like this, the task of photometric calibration is to recover this F, E, and V such that we have a calibrated sequence like this, where the corresponding part should have similar or the same pixel intensities. To do photometric calibration, if you use previous approach, you need a quite strict lab setting. For example, if you want to calibrate the response function, then you need to mount your camera to a tripod, and you need to take around 1,000 images of a static scene. And also, you need to be able to control the exposure time of the camera. Another thing is you need to make sure the scene covers a wide range of intensities. To recover the vignetting, you need to take another extra hundreds of images of a bright planar surface, which needs to be fully Lambertian. And most of the time, you also need an AR marker and a pipeline to estimate the camera pose. And depends on the image resolution, the entire approach can take up to 10 minutes. In practice, if you are lucky, you have the access to the camera, then the previous approach is still quite tedious to do because, I mean, you need to fulfill basically all the requirements there. And most of the time, it's not possible, like you can control the exposure time of your camera. So what people really want is a pipeline which can be used in a plug-and-play mode. What happens more often in practice is a lot of time we don't have the access to the camera. For example, nowadays we have many public datasets which usually don't provide photometric calibration information. And meanwhile, we have millions of videos online where we have no information about the camera at all. So in this work, we want to solve these problems. So we want to provide a pipeline which you can just run it, and it will calibrate the camera automatically for you. So here I use a simplified example to show the formulation of photometric calibration. We have one 3D point here, which is observed by 3 images. And if you plug the variables into the image formation equation, then we have these 3 constraints, and which can be reformulated to this nonlinear least square problem. And here, basically, we want to measure the measured pixel intensity O here with the predict one, like using this all the 3 photometric factors. And we use Hubbell norm here, and also some kind of weighting to downweight pixels with high gradient, image gradient. And then if you have a set of points and you have a set of images, you just sum up all the energy factors of all this. Before moving to show the result, I want to devote a few pages on shortly introducing some technical details, which I think might be useful to other people who want to work on this topic. So our system consists of a tracking front end and an optimization back end. So for the front end, the first question needs to be considered is, so which points should we track? The requirements here are the sampled points should cover a wide range of intensity and also a wide range of radio in order to recover the response function and the vignetting factors. In other words, we need to sample points as uniformly distributed as possible. So we thus propose to discretize images to regular grid, and then out of each grid cell, we try to sample a fixed number of points. The second question is how to track the sampled points. The first idea came into our mind is to use the standard KLT tracker. But since it's also based on the brightness constancy assumption, which we don't have before our calibration, tracking will fail when there is brightness change between consecutive frames, as shown on the left side. So it's kind of a chicken and egg problem. So in our case, we use an improved version of the KLT tracker, which we call it gain adaptive KLT tracker. The idea is we take the photometric factor into consideration, and if we ignore vignetting, the ratio of the accumulated radiance should be equal to the ratio of the exposure time, which we consider as one extra parameter to optimize. The last detail of the front end I'd like to mention is outlier filtering. So we propose to use 2 filters. The first one is a bidirectional filter, which tracks features from image I to image I+1 and then backward, and filter out points with large displacement. The second filter, we consider the motion field is locally smooth. So we filter out points with locally inconsistency motions. As shown on the bottom, most of the outliers can be successfully removed. For the optimization backend, one thing worth mentioning is the parametrization of the response and the vignetting. For response function, we use the empirical model of response. So the idea is you gather the response functions of many real cameras, then you perform PCA. So afterwards, you can use the linear combination of the response components to basically represent any camera response function. And for vignetting, we use the radio vignetting model, which is a polynomial, and we further assume center of the vignetting is overlapped with the center of the images, which in practice is not always the case, but in our case, it works fairly well. So what about the speed? So here I show a table summarizing the runtimes of each part. It is worth noting that there is no need to optimize for the response and vignetting for each new image frame, because usually in practice they are almost constant for each camera. So we therefore only optimize the exposure time for each new frame and use a separate thread to optimize for response function vignetting in the background. Also, our code is not super optimized, so I believe the runtime could be further improved. But it can already run in real time. We've applied our method to 3 public datasets. So here we first show the result on the ICRA simulated dataset. We apply artificial photometric distortions to the sequence and show it on the left side. On the right is the calibrated sequence with the tracked features. So on bottom, we show the live evolution of our estimations. So as you can see, all estimations converge to the ground truth very fast. Here is a comparison of the 3D reconstructions delivered by DSO. As you see, without using our method, DSO almost doesn't work on the distorted sequence. And with our online calibration, it can give fairly sharp reconstructions. In the second video, we show the result on the 2 mono view dataset, which has real photometric distortions and also provides ground truth for them. Similarly, as before, all the estimations quickly convert to the ground truth. We further show the result on the Europe dataset, which doesn't provide any information for photometric calibration. As our method doesn't require the access to camera or specific calibration sequence, we simply run it online with DSO. And here you see the results of the estimated camera trajectories and the 3D reconstruction. On bottom, we show the errors of running DSO 10 times on this sequence, and it consistently performs much better with our method. To summarize, photometric calibration is important, and there are a lot of limitations of the previous approach for photometric calibration. So we propose an online photometric calibration which can estimate the 3 photometric factors online, and you can use it in a plug-and-play mode, and it doesn't need the access to the camera. And it improves the result of DSO significantly. And our code is just online. You can search for online photometric calibration on GitHub. Please have a look and give us some feedbacks. Thanks.
Time for one question. Since your technique is kind of independent of the application domain, did you try it in different application settings?
No, we only tried for DSO for our case. But since it's totally separated from the DSO, so basically you can use it for other methods.
This one very quick one.
Actually, we have some plots shown, I think, there. I think. Okay. And to give you the quick answer, it performs almost the same. I mean, the calibration and also the visual odometry performs almost the same. Thank you.
All right, thanks again.